Okay, let us continue. So our second speaker today is Edouard Daviaud, and his title is Mass Transference Principle, Diophantine Approximation of Fractals. Please.
So first, thank you, Sasha and Antti, to give me the opportunity to talk at this seminar. So the title is Mass Transference Principle, a Diophantine Approximation on Fractals. So first of all, I will abbreviate quite quickly Mass Transference Principle in MTP, because it's easier to say. And then, so first, I will introduce the problem that I would be interested in. And in the second time, I will present the result that I had in the case of self-similar fractals. And I will briefly state a sketch of proof in which there will be a certain MTP that comes into play. And that will transition to the last part where I will speak a little bit more about MTPs for finite measures. Okay. So let's start with the introduction. So I will start by defining what, let's say, a fractal set is. So if you take a compact set X included in RD, and you give yourself some contracting maps F1, Fm, then it is known that there is a unique compact set K, which satisfies that K is the union of the Fi of K. That is the attractor of the IFSS. That is the fractal that we consider. And we also have the property that if you consider any point x0 in X, you can obtain K as the limit in a Hausdorff topology of the union of the point of the orbit under the IFSS of the point x0. So here the map Fi bar denotes the composition Fi1, Fin if the word I bar was I1, In. So in particular, this say raises the natural question of giving a notion of speed rates of approximation of a point x of k by the orbits Fi bar of x0. So this is done doing the following. So first, a quick observation. If you consider x0 to be a point of k, then you have that k is the intersection of the union of every word of length n of the ball Fi bar of x0 and with radius Fi bar of k, the diameter of Fi bar of k. So in other words, that's just the lim sup of those balls. And there, a very natural way to let's say to define the notion of speed rates of approximation of a point x in k is to define the following. So for x, a point of k, we say that x is approximable at speed rate delta by x0 if the point x is in the lim sup of those shrunk balls b Fi bar of x0, and instead of Fi bar of k, you take the smaller radius Fi bar of k power delta. So there is less points in this lim sup set that we call W delta x0. And we will be particularly interested in the dimension of the set W delta x0. So we will speak about the case where the IFS is self-similar. So the quantity that plays an important role in the dimension theory of self-similar fractals is the similarity dimension of an IFSS. So an IFS, a self-similar IFSS, given a self-similar IFSS, you define the similarity dimension of the IFSS as the real number that satisfies this equation there, where the Ci are the contraction ratio of the map F1 Fm. Okay, and how does it come into play in the estimation of the dimension of an IFSS? So the only known cases of for instance, the only known cases of self-similar IFS on R, which satisfies that the other dimension of K is not the minimum between 1 and the similarity dimension of the FSS, is when you have exact overlaps, which means that you have two, let's say, composition maps that turns out to be equal with different words. So I'd say it's a very natural candidate for the dimension of an AFS in RD is always minimum between D and a similarity dimension under reasonable assumption, let's say. Let's put it this way. So the theorem that I want to speak about is the following. So if you assume that the dimension of the attractor K satisfies that the dimension of K is the similarity dimension of the self-similar AFS you consider, then for every point x0 in the attractor K, you get that the other dimension of the set W x0 delta is the dimension of K divided by delta. So let me give, so it's really not restrictive, this assumption. So let me give some example of AFS for which this holds concretely, and some restriction also. So first, if you consider any AFS that satisfies the open set condition, then it is known that the AFS satisfies that the other dimension is the similarity dimension. But in this case, the result follows directly from the mass, from the MCP, from Beresnevich and Bellany. And I think the dimension result was established in first place by Hill and Bellany. So more example, let's say, that are maybe a little bit less restrictive in terms of assumptions. So if you take any self-similar AFS on R, which satisfies the exponential separation condition or with algebraic contraction ratios and no exact overlap and similarity dimension smaller than 1, you also satisfy that the dimension of the attractor is the similarity dimension. So this provides, say, a great number of explicit examples, for instance. You can give some of them. It's also generic in a sense. So in the following sense, so if you fix some contraction ratio C1, Cm, such that the similarity dimension of the AFS that you will build is smaller than 1, so you satisfy this inequation. Then for a Lebesgue almost all translation, A1AD, sorry, that should be an N there instead of a D. Oops. The map F1 of x equals C1x plus A1 and Fm of x equals Cmx plus An also satisfies that the other dimension of K is equal to the similarity dimension. And in particular, you can apply the theorem above. A restriction to this, so if the similarity dimension is strictly larger than the dimension of the space, it can be, so you can build some AFS such that if you keep on shrinking the targets for a certain range of delta in a, let's say, non-empty interior interval, you still get the dimension is D. So for instance, there is an explicit example of this in an article of Baker. But it's not too hard to understand that if you, let's say, if you allow yourself to get a very large similarity dimension, you can, let's say, give yourself so many similarities that if you keep on contracting the targets, then you still cover a set of positive Lebesgue measures. That's what's happening here. Okay, so there are also some examples of in RD in general, in a higher dimension, but my slide was full, so I decided to drop it. If someone is interested in this, he can ask me. So let me give a short sketch of proof for this result. So first, the upper bound. So for the sake of simplicity, just assume that the AFS is homogeneous. So you have all the same shrinking rates. And so how you estimate the upper bound? Well, you consider the cylinder I bar, given the, let's say, and you define the measure nu I bar which correspond to the similarity dimension, which means that this measure is associated with the probability vector P1 equals C1 power dimension of S and PM equals Cm power dimension of S. Okay, and then you have this very straightforward computation, which is the following. If you sum on every word I bar the diameter of the ball of your limb subset, power dimension of S plus epsilon divided by delta. So you really write the computation straightforwardly, and you will get that this sum there converges. Okay, so this computation is very straightforward, and let's say the important consequence of this computation is the following. So if you in particular, so since this sum converges there, then the rest goes to 0. Okay, and for every large n, this lim set is always included in the union of those balls that you know the sum is going to go to 0, and they have very small radius. So in particular, this gives you that the Hausdorff measure of the set W x0 delta at the exponent dimension of S plus epsilon divided by delta is 0. And from this, you deduce that the other dimension of W x0 delta is smaller than the similarity dimension divided by delta. Okay, so this was for the upper bound. So we see that it's quite straightforward. And so the hard part is actually the lower bound for this theorem. So let me give also a sketch of proof of the lower bound. So let me first recall what a set similar measure is. So if you have an IFS T, that is T1 TT, and a probability vector P1 PT, then the self-similar measure associated with T and the probability vector P1 PT is the measure that satisfies this relation, mu equal to the sum of the pi mu Ti bar minus 1. Okay. And so it is important in our case because we have the following variational principle. So let me recall first that those measures, they are exact dimensional. And we have the following variational principle. So we go back to our problem where the IFS was S. For every epsilon positive, you have some. You can find some words I bar 1 and I bar n, and a probability vector P1 Pn, such that the attractor of T epsilon associated with those map Fi bar 1, Fi bar n is K. So the attractor of the IFS S we consider as start. And you can also find a set similar measure for this IFS T epsilon, which satisfies that the dimension of this measure is roughly the dimension of the attractor. Okay, so once we have this variational principle, the lower bound actually relies on a MTP for set similar measures. So if you consider mu a set similar measure, and Bn a sequence of balls that is centered on the attractor K, if the lim sup has full measure, then you obtain that the outer dimension of the lim sup of the shrunk balls is larger than the dimension of mu divided by delta. So in particular, in our case, this allows us to, in combination with the previous variational principle, to obtain the lower bound that we want. So how do we do this? We fix epsilon positive. We consider the self-similar measure that we have in our variational principle, that we know that the dimension is larger than the dimension of K minus epsilon. We already noticed that W x01 was K. That was the first remark. So in particular, it has very much full measure. And then for every delta, we have that the other dimension of W x0 delta is larger than the dimension of K minus epsilon divided by delta. If that's epsilon go to 0, you get the bound that you want. So the hard part of the proof of this result is actually this MTP there. The key point is this MTP there. So let me speak about MTP in general. So I will do a very quick historic of MTPs. So I will present 3 of them. It's not much. So the idea of MTPs is to get lower bounds for the outer dimension of lim subsets. And the name MTPs was given by Beresnevich and Bellany for this particular theorem. So if you have K, a compact set that is equipped with an S alpha regular measure mu. So alpha regular means that the measure of each ball centered in Pi is roughly the diameter of the ball power S. If you have a sequence of balls that satisfies that the lim sup has full mu measure, then for every delta larger than 1, you get that the Hausdorff measure at the critical exponent S over delta is infinite. Or you can also, it is true in every ball certain case. Okay. In particular, you get that the dimension is larger than S over delta. There are a little bit two directions in which we may want to extend this theorem. First, we may want to ask less about the measure than being alpha regular. So this was done by Barry and Sorel, for instance. So in our statistics, they prove that if you have a multinomial measure, so let's say a self-similar measure that is associated with a carpet, a self-similar carpet, and you have a sequence of balls that is centered on the support of the measure, then you have this MTP there. So if the lim sup has full measure, then the other dimension of the lim sup of the shrunk balls has a dimension, at least the dimension of the measure divided by delta. So another direction in which we may want to extend this theorem is we may ask, let's say, may want to consider other sets than shrunk balls B and delta, and consider, for instance, rectangles or other open sets. This was done in the case of the Lebesgue measure by the theorem of Koivu-Salo and Rams. And the important geometrical quantity that comes into play in this theorem is the following: the Hausdorff content of a set E, which is defined as the smallest of the sum of the diameter of n power s, where n is a covering of E by balls. So no restriction on radius there. And the theorem they obtain is the following: if you consider a sequence of ball Bn and a sequence of open set Un, with Un that is included in Bn, if the lim sup of the Bn is full, then the Hausdorff content of the and if the Hausdorff content of the set Un is larger than the Lebesgue measure of the ball Bn, then you get that for such an S, such an S is always a lower bound for the Hausdorff dimension of the lim sup of Un. So in particular, for instance, if you take Un to be a rectangle, you can compute explicitly this quantity, the content of a rectangle, and then you look at let's say you solve the equation that gives you that S at the critical exponent S, you recover diameter of Bn power delta, and you have the lower bound for the dimension of those rectangles. So you recover the theorem of Wang, Wu, and Chu. So I will present MTP that holds for any finite measure. So the same type of MTP of Koivu-Salo and Rams, but instead of the Lebesgue measure, you have only a finite measure. So in this case, the key geometric quantity to consider is the following. So if you have a set E, you define the essential Hausdorff content of a set E to be the smallest of the Hausdorff content of set A, including E with same measure as E. Okay, so this is this is what it is. So it's the smallest of the content of set of full measure inside the set. And so the MTP that we get in this, let's say, in this context is the following. So this will be a long theorem. Okay, so but don't worry about it. So you have a sequence of ball Bn and a sequence of open Un. So there are a little bit two effects that can make your dimension, let's say the dimension of the lim sup Un being be large. So first of all, you may have to begin with, you may have taken both Bn that overlaps a little bit too much. So you may have, say, a little bit artificially many sets UN. In order to deal with this phenomenon, you need to introduce those sets U tilde n that will take into account all the sets UP that you obtain by so there is something missing there. So the union of the UP for the ball BP that have roughly the same radius as n, but that intersects Bn. So there should be a BP intersect Bn. Okay, that is missing. So you count all of them, and then the result that you obtain is so you give yourself a finite measure mu. Okay. So if you assume that a probability measure, sorry, not only finite. If you assume that the lim sup of 1/2 of Bn has full mu measure, okay, and you assume that the essential Hausdorff content of u tilde n is larger than the measure of 3Bn, then you get that the Hausdorff dimension of the lim sup of un is larger than S. And let me add that you can, using an extraction theorem, you can actually show that you lose nothing by let's say, assuming that the measure of 3Bn is always the diameter of Bn power the dimension of the measure mu, the lower dimension of the measure mu. So this gives you a lower bound. Let me also remark there that since this the lim sup of Bn has full mu measure, and the essential Hausdorff content is the smallest of the content of set A with full measure inside A. In particular, this gives you that you notice if you satisfy that, you also satisfy that the essential content of u tilde n intersected with the lim sup of the ball BP is larger than the measure of 3Bn. And so you get also an upper bound in the following sense. So if you assume now that the Hausdorff content of the set u tilde n intersected with the lim sup of the ball BP is smaller than the measure of 3Bn, then such an S is always an upper bound for the other dimension of the lim sup of the UN. So you have both ways. You have a lower bound and an upper bound. So it all comes down to be able to estimate this quantity there to establish MTPs, the essential Hausdorff content of open sets. In the case of a set similar measure, you can actually estimate it quite precisely, regardless of any separation condition. And so the result that you get is the following. If you consider mu to be a set similar measure, then for every ball and every open set centered for every open set and every ball centered in K, you get the following results. So if S is larger than the dimension of the measure, you get that the essential Hausdorff content is 0. So this is straightforward from the definition. And when S is smaller than the dimension of the measure, the essential Hausdorff content of any open set is the Hausdorff content of the open set intersected with the attractor K. And the essential Hausdorff content of any ball B is roughly diameter of B power S. So let me also say that to prove this, you first prove the third point, and then the second point is automatic with the third point. So in particular, notice that if you take mu to be the Lebesgue measure, well then K there is only is 0 and power D. Okay, so this is only the Hausdorff content of omega, and you recover Koivu-Saloram's theorem. If you let me also notice that if for every delta larger than 1, if you apply this equality there to the ball B delta, then you get that the essential Hausdorff content of at the critical exponent dimension of mu divided by delta of the ball B delta is roughly diameter of B power Hausdorff dimension of mu. Okay, so in particular with this equality there and this condition there that is satisfied, both of it gives you the MTP for such similar measures. So we roughly, let's say, finish the proof of the statement that I had slide 3. Okay. So maybe one last corollary that I would like to highlight is the following. So in the case of the mu of the Lebesgue measure mu, sorry, in the case where mu is the Lebesgue measure, we have the following results. So if you consider a sequence of ball Bn and a sequence of open set Un, so that Un is included in Bn, and you assume that the lim sup of Bn has full Lebesgue measure. If it turns out that you have a critical exponent S for which the Hausdorff content of the set U tilde n is roughly speaking the Lebesgue measure of the ball Bn in the sense that it satisfies this equation there. Then you know that such an S is always this S is the dimension of the new sup of Un. And finally, if you know that every ball Bn with let's say radius roughly 2 power minus k intersects not too much other ball Bp, so intersect less than 2 power petit o of k balls Bp with roughly the same radius, then you can actually replace in this equation, you can replace U tilde n by only Un. So you get something that is cleaner. Okay, so, and I think that's all I have to say. So, yeah, no, I have one last thing to say. So the similar, you can also state something similar for such similar measures by, let's say, replacing this quantity by the Hausdorff content of U tilde n intersected with the attractor of the IFS.
Okay, thank you very much. Are there any comments, questions?